Welcome to this lesson on data structures. So far, you've dealt with variables representing individual basic data types, like integers, floats, booleans, and strings. In this lesson, you'll learn how to group and order these data types into different data structures, namely lists, tuples, sets, dictionaries, and compound data structures. You'll also learn about the last two types of operators in Python, membership and identity, along with more built-in functions and methods. Let's get started. We've seen individual pieces of data, like a string or a number. These are great, but Python's capability to write powerful programs is maximized when we can work with something called containers of data, which contain other data types and even other containers. So let's introduce our first Python container, lists. A list is a data structure in Python that is a mutable, ordered sequence of elements. More on the mutable ordered part later. This code defines a variable, months, which contains a list of strings. Each element in the list is a month of the year. A list is defined using square brackets and always holds other data, which are separated by commas. This data could be a mix of any of the data types you've already seen. Lists have an order, or more appropriately, are ordered. We can look up individual elements in the list by their index. We can look up values in a list like this. We type in the list name, followed by square brackets, with an integer indicating its position, or index. Notice that the first element in the list, January, is located at index 0 rather than index 1. Many programming languages follow this convention, called zero-based indexing. If zero-based indexing is confusing, consider it this way. An element's index describes how far the element is from the beginning of the list. The first element is 0 elements away from the beginning. The second one is 1 element away, and so on. We can also index from the end of the list rather than the front like we've been doing so far. To do this, we use negative indices. For example, we can get the last month of the year. The index -1 refers to the last element of the list, -2 to the second to last, and so on. Note that while 0 is the first index of the list, -0 is not the last, which can be a bit confusing. If you attempt to access an index in a list that does not exist, you will get a list index exception. This is Python's way of telling you that you are trying to access an index that is not in the list. Since the index 25 does not exist, we received this error. Getting index errors is quite common, especially if you're not used to indexing in Python. You might get these errors quite a lot in the beginning. The most common reason for getting an index error is using an index that's off by 1. But there may be other reasons why you would get such an error. It is always a good idea to use the print function and debug with a small example. This can tell you if your indexing is off and by how much. In addition to accessing individual elements from a list, we can use Python's slicing notation to access a subsequence of a list. Slicing means using indices to slice off parts of an object, like a string or a list. An example makes it super clear. Again, consider this list of months. We can slice the third quarter of the year from the months list like this. The index to the left of the colon, 6, is where the slice begins. The slice continues up to the second index, 9. Notice that the 6 is the index of July, but 9 is the index of October. The lower bound is inclusive, but the upper bound is exclusive. There are a couple of slicing shortcuts that simplify common situations. If you would like to make a slice that begins at the very beginning of the original list, you can omit the starting index like this. Or, if you'd like to make a slice that ends at the very end of the original list, you can omit the ending index like this. List is a type, just like string, float, and int. Of the types we've seen, lists are most similar to strings. Both types support the len function, indexing, and slicing. Here, you can see that the length of the string is the number of characters, and the length of the list is the number of elements it holds. And zero indexing is supported for both, as well as slicing based on the indices shown here. Another thing they both support are membership operators, in and not. In evaluates if the object on the left side is included in the object on the right side, and not in evaluates if the object on the left side is not included in the object on the right side. Here, we can check if the string her is in this string, which is right here. However, Sunday is not in our list, as it only holds the months. So how are lists different from strings? You saw that both support indexing, slicing, and the in operator. The most obvious difference is that strings are sequences of letters, while list elements can be any type of object. A more subtle difference is that lists can be modified, but strings can't. Here, we can change the fourth element, index 3, of this list to Friday if we want. But here, we get an error if we try to change the third element of a string. The technical term for whether an object can be modified after its creation is mutability. We can modify the values of lists, so a list is a mutable data type. We can't modify strings, so a string is an immutable data type. As we introduce more data types, there are two factors that we will continue to consider. One is mutability, and the other is order. Order is whether the order of contents for an object matters, and whether or not parts of the object can be accessed using this order. Both strings and lists are ordered, which is why indexing works well for them. However, one is mutable, while the other is not. We will see more data types that fall under different sections of this grid as we continue. For now, we'll explore the methods and functions that work on lists, and we'll take advantage of list mutability in our programs. Previously, when we created a variable that held an immutable object, the value of that immutable object was saved in memory. Here, we create a name with value Jim and assign it to another variable called student. It is the value Jim that is assigned to student. So when we reassign name to update it to Tim, this change is not reflected in the value of student. Lists are different from strings as they are mutable. Here, we create a list of scores and assign this same list to the variable grades, B, C, A, D, B, A, 6 of them. And when we change or mutate the scores list, making the fourth grade B instead of D, this affects both scores and grades. Both scores and grades are variable names for the same underlying list, and either name can be used to access and change that list. The behavior of variables containing mutable and immutable objects are very different and might even seem surprising at times. Experiment. Use the print functions and double-check your work where you can to make sure that your programs correctly keep track of their data. While you experiment with lists, there are some useful functions you should get familiar with. Len returns how many elements are in a list. Max returns the greatest element of a list. How the greatest element is determined depends on what type of objects are in your list. The maximum element in a list of numbers is the largest number. The maximum element in a list of strings is the element that would occur last if the list was sorted alphabetically. That's reticulated Python for this list. R is the largest letter alphabetically. In other words, greater than B, A, B, and A. This works because the max function is defined in terms of the greater than comparison operator. The greater than comparison operator is defined for many non-numeric types. If you're working with objects that can be compared with this, then you can use max on a list of the objects. For strings, the standard comparison is alphabetical, so the maximum of this list is the element that appears last alphabetically. Although you can create lists that hold a mix of elements of many types, as you see here, integers and text, the max function is undefined for lists that contain elements from different incomparable types. Here, you can see it breaks with this mix of data types. Min is the opposite of max and returns the smallest element in a list. Sorted returns a copy of a list in order from smallest to largest, leaving the original list unchanged. Here, for a list called sizes, the order is ascending. You can sort from largest to smallest by adding the optional argument reverse equals true. Now the order is descending. Let's introduce a new string method that works with lists. Join. Join takes a list as an argument and returns a string consisting of the list elements joined by a separator string. In this example, we use the string \n as a separator so that there is a new line between each element. For, new line, aft, new line, starboard, new line, port. We can also use other strings as separators with join. Here, we use a hyphen. It's important to remember to separate each of the items in the list you are joining with a comma. Forgetting to do so will not trigger an error, but will also give you unexpected results. In the example below, omitting a comma between Garcia and O'Kelly results in the following. Notice how the hyphen separator is missing between Garcia and O'Kelly, and instead the two strings were appended. This happens because of Python's default string literal appending. If join returns different results than expected, check for missing commas. Also, note that join will trigger an error if we try to join anything other than strings. We get an error here because an integer was included in the list. Lastly, a helpful method called append adds an element to the end of the list. Next, you'll practice working with lists and explore more list methods. Python provides another useful container, tuples. Tuples are used to store related pieces of information. A tuple is a data structure in Python that is an immutable, ordered sequence of elements. Consider this example involving latitude and longitude. Tuples are similar to lists in that they store an ordered collection of objects which can be accessed by their indices. For example, location 0 and location 1. Unlike lists, however, tuples are immutable. You cannot add or remove items from tuples or sort them in place. Why do we have tuples if they're like lists with fewer features? Tuples are useful when you have two or more values that are so closely related that they will always be used together, like latitude and longitude coordinates. Tuples can also be used to assign multiple variables in a compact way. Notice that the values assigned to the tuple dimensions aren't surrounded with parentheses as previous examples were. The parentheses are optional when making tuples, and programmers frequently omit them if parentheses don't clarify the code. In the second line, 3 variables are assigned from the content of the tuple dimensions. This is called tuple unpacking. You can use tuple unpacking to assign the information from a tuple into multiple variables without having to access them one by one, and make multiple assignment statements. In this example, if we won't need to use dimensions directly, we could shorten those 2 lines of code into a single line that assigns 3 variables in one go. Imagine that you run a popular search engine and you've surveyed your users to see where they're browsing from. You've collected the 785 responses and have assembled them into a list of countries. There aren't 785 countries in the world, which means that there are duplicate entries in the countries list. Slicing the list to see the first few elements confirms this. It would be useful to remove the duplicates to produce a list of all of the countries that users browse from. Well, a set in Python does exactly that. Sets are containers of unique elements without any particular ordering. We can create a set from a list like this. Set removes the duplicates, and the print function prints the unique values of which there are 196 countries. Sets support the in operator the same way lists do. India is in this set. You can add elements to sets, but you don't use the append method like you do with lists. Instead, sets have the add method. Here, Italy is added. Sets also have a pop method, just like lists. When you pop an element from a set, a random element is removed. Remember that sets, unlike lists, are unordered, so there is no last element. Other operations you can perform with sets include those of mathematical sets. Methods like union, intersection, and difference are easy to perform with sets and are much faster than such operators with other containers. Sets are simple data structures, and they have one main use: collecting unique elements. Our next data structures, dictionaries, are more flexible. Rather than storing single objects like lists and sets do, dictionaries store pairs of elements, keys, and values. In this example, we define a dictionary where the keys are element names and their values are their corresponding atomic numbers. We can look up values in the dictionary by using square brackets enclosing a key. We can also insert new values into the dictionary with square brackets. Here, we are adding lithium and giving it a value of 3. Dictionary keys are similar to list indices. We can select elements from the data structure by putting the key in square brackets. Unlike lists, dictionaries can have keys of any immutable type, not just integers. The element dictionary uses strings for its keys. However, it's not even necessary for every key to have the same type. We can check whether a value is in a dictionary the same way we check whether a value is in a list or set with the in keyword. We can use in to verify whether a key is in the dictionary before looking it up, if there's a possibility that the key is not there. Mithril was not part of our elements dictionary, so false is printed. Dictionaries have a related method that's also useful: get. Get looks up values in a dictionary, but unlike square brackets, get returns none, or a default value of your choice, if the key is not found. The lithium is not in our dictionary, so none is returned and then printed. If you expect lookups to sometimes fail, get might be a better tool than normal square bracket lookups because errors can crash your program, which isn't good. You can check if a key returned none with the is operator, or you can check for the opposite using is not. These are called identity operators. You will learn more about identity operators and how they differ from using these equals to or not equals to comparison operators in the quizzes that follow. In the elements dictionary we saw earlier, element names, which are strings, are mapped to their atomic numbers, which are integers. But what if we wanted to store more information about each element, like their weight and symbol? We can do that by adjusting this dictionary so that it maps the element names to another dictionary that stores that collection of data. We can look up information about an entry in this nested dictionary in the same ways we did before, with square brackets or the get method. We can look up specific information from the helium dictionary like this. This code is first looking up the key helium in the elements dictionary, producing the helium dictionary. The second lookup, weight, then looks up the weight key in that helium dictionary to find helium's atomic weight.